Hey, 12th graders. So we are finally going to actually talk about calculus. So we're going to learn about what the derivative is. And calculus, if we wanted to really explain it in a really quick way, calculus has two branches. One is about derivatives and one is about integrals. Integrals and derivatives undo each other. They mean a lot of different things conceptually, so it's kind of hard to see why they undo each other. But for right now, we're just going to understand that addition, subtraction, multiplication, division, they undo each other. So we're going to talk about derivatives and what it means conceptually, which is, hey, what we've been doing this whole time. What we've been talking about so far is this idea of a limit, and more specifically, the idea of a limit when combined with the idea of the slope of a curve at a given point. In other words, the tangent line that you can draw on a curve, and what is the slope of that tangent line, which represents the slope at that point of the curve. So the derivative of a function, it is a function. So your derivative is a function as well. And it's a function that gives you the gradient of the tangent line. So what we've been doing so far is we've been drawing in our best guess of the tangent line and then going in and finding 2 points on that tangent line and using our slope formula to be like, what is the slope at this 1 point for the tangent line at any point? And the derivative is really cool because, first of all, it just does it for you and just tells you what the slope would be of the tangent line at any point. So instead of saying, we're going to pick this 1 point, we're going to draw our best tangent line, your derivative says, hey, you just tell me where the point is, and we can plug that point into this function, and I'll tell you what the gradient is at that point. So it has some ideas that goes with it. This is like a brand new idea for you guys. So if I were to draw something that looks like this, it's a line, first of all, right? A line. A straight line is redundant because all lines are straight. So f of x equals, we're going to call this 1/2 x plus 5. And if I wanted to find the derivative, in other words, the slope of the tangent line at any given point, for this function, realize that since it is a straight line, the slope will always be the same, right? So the slope of your tangent line will always be really just the slope of this line. So I could tell you right now that the derivative of this, which is notated like this, f prime. So notice it can be really, really close to your inverse symbol with the -1, but it's not a 1 up there, it's a prime. So I skipped something here that's very important, all the different ways that we denote the derivative. So we have f prime of x, or we have dy over dx, which is the derivative of y with respect to x. This is notation you see a lot, I think mostly because it looks really smart, but I think it can be really confusing. I think I didn't really understand what this meant in a lot of ways when I first started learning about calculus because we went so quickly into things that I just didn't understand it. All it means is the derivative of y with respect to x. Or you could just do something super simple and call it y prime. So those are all the different ways that we use to write about the derivative. And so you'll see all different ways with respect to that, writing throughout these notes. So going back to this, the derivative of a line is just the slope of the line. So it just gives you back a number. Hey, the slope of the tangent line of this line is just the slope of the line. It's just a number. It's always 1/2. The slope is always the same. It's a constant rate of change. And so your derivative is 1/2. Versus most other things that we do, which we call curves, right? You've got lines, which are straight by definition because it's a constant rate of change. Your curves could be anything. I'm going to draw a parabola just for the sake of ease. And I'll give this an arbitrary let's do, oh no, sorry. Let's do 4. So this is the original function. And so if we want to talk about the gradient of a tangent line, we would have a gradient here that would be different. And then as we get closer to the vertex, right, that gradient starts to level out and get closer to 0, right? This is a gradient of 0 at the vertex. versus a positive gradient here versus a negative gradient on the other side. So your gradient, your slope on this curve is constantly changing because it's not a constant rate of change. So when we talk about the derivative of this function, which is negative 2x plus 4, we'll learn how to find that in your next notes, but it's pretty straightforward. So the derivative of this function is another function, because if I wanted to know what the slope was at this point, it would be different than the slope at this point. And so if I wanted to know what the slope of that tangent line was, I would just have to plug that information into this function to get me that slope. So that's kind of the idea of how we talk about derivatives. Derivatives are just the gradient of a tangent line, and they're really important for knowing like when is the slope of this function positive, when is it 0, and when is it negative, right? So having positive would be something that looks like this at any point, right? It doesn't have to be a line, it doesn't have to be straight, but anything that's just going up at any point. Versus 0 is either a flat line, your tangent line would be flat, or it's a vertex, right? This would have a tangent line with a gradient of 0. And then negative is anything that's decreasing. It could be decreasing a lot, right? Like here it's decreasing a lot at first, or it could be decreasing a little bit at a time. But we're just looking for these slopes that are behaving in that way. So that's the general idea of derivatives, and we're going to practice it with 3 examples.